I feel like a lot of my work has been before and after style visual analysis with high res. So stuff that is not spectrally, there's not a lot of spectral bands to deal with. There's not a lot of temporal resolution. There's a lot of spatial resolution. And so you can do, visual analysis, like look at this thing after, or build a model or train a model, right? And deploy and find these things. But more recently, I feel like I've been using more information from longer time series, and I thought it would be a good opportunity to talk about time series, dense time series, and why that is maybe still underappreciated. I don't know.
Yeah, I definitely agree that it's underappreciated. I mean, the first time I looked at like Landtrendr outputs, this is the kind of stuff you're talking about, right? Like sort of long time series. I mean, Landtrendr is like one observation per year, so it's not. I don't know if you could really qualify that. You
boil down a bunch of decades. But you boil down a bunch of observations into a single statistic from the year. You boil it down into one observation, but you get to decide how you do that.
Yep. Yeah. And I just remember running this over the state of Mexico. There was like some project about change detection over New Mexico. And I don't know, it's just kind of astonishing how much stuff just popped out, actually. And I think I had chosen like the NDVI metric or something.
Okay, so you've got some Landsat based annual thing you've calculated over New Mexico, and then you've chosen NDVI as your metric. So then you've got a 40-year time series of NDVI. You're running a Landtrendr to basically then find these breakpoints, right? Or like these
breakpoints.
This baseline period, this transition period, and then this new stable period, if that's a way to simplify it. So you're saying then you have all these different classes of changes, right, that come out of NDVI.
Yep.
And so so you're looking through all these different classes.
So not necessarily class. I think I'm assigning the class myself by looking around, but even picking something like NDVI, because you have to like reduce, and it's been a long time since I've looked at Landtrendr outputs, but even after you've run the algorithm, in order to visualize it, you need to choose like a reduction over the results of the algorithm, like year of greatest change, or like greatest NDVI change, or
it's like positive change or negative change.
Exactly.
Yeah,
yes.
You have to choose your transition. Exactly. Yep.
Yeah, and so it's still too high dimensional for you to just throw onto a map.
15 dimensional thing. Yeah.
Yeah, and even that's the reduction.
Yeah.
And then I think I just looked at something really simple like greatest NDVI loss, maybe. No, it was year of greatest NDVI loss. And it's just like this temporal segmentation thing is just crazy. Like, first of all of the burn scars definitely appear. Like, you could just see, like, like Hermit's Peak, and then, like all of the different fires that have, kind of experienced. And then, but not just that, like, then you go to like the south east, and now you like the well pads pop up, even though they're not necessarily NDVI related. It's just that like there
NDVI
was maybe
is a great proxy for well pads or built areas.
There was just like some vegetation there before, like these juniper bushes, or this, probably not even juniper down there, and then there was absolutely none,
just sage brush.
Yeah, and the changes, the year of the change is spatially coherent because it's the year the well pad was built or something like that. And so, it's, I don't know, I was sort of astonished, and I kind of have felt the whole time, not to bring back embeddings again, just that like if a set of embeddings could do... couldn't help myself. But not to derail this too much,
It's
but
over. You
just
already
that if
derailed
someone
it. We're done.
if someone if someone could make a set of embeddings that reproduce like Landtrendr outputs as easily as Landtrendr does, I think that would be like considered like a huge success. And so I'm always kind of like, well, I mean, we already have the thing that you think embeddings can do in a lot of ways. So
Yeah.
anyway, that was my experience. Yeah.
I'm so glad you brought up the NDVI change in the Landsat in 40 years, because that's just actually exactly what I did when we did our West Bank piece last year. Literally the exact same thing. I chose NDVI as the metric, had the Landsat collection 2 time series, and I looked for NDVI loss, and I looked for the year of NDVI loss. And
Yeah.
I did some post-processing after the fact that to sort of like go back in time to clean things up. Because Landtrendr can be so general, right? It's this problem of like you find the burn scars and the well pads. But for me, I basically constrained the problem after the fact. But basically, Landtrendr does all the hard work to, in my case, do this urban expansion over time.
Yep.
And so that was my first time actually using Landtrendr for something real. And it's just so much more scalable than because it's just so general in the formulation, right? So it's like it's kind of up
so
to
simple.
you to like pick your trajectory that you look for within the outputs of Landtrendr that fall out. But yeah, truly incredible. I don't know. I was blown away too.
Yeah. What implementation did you use?
Like I used the Earth Engine implementation.
But like the LTG, like I think it's by like Justin Bratton. Like,
yeah.
Like the Python package. Okay.
Is it Python? I mean, it's available on the JavaScript stuff too, right?
Yeah. So I used the code editor to run it because it was just like all in there. Yeah, it was like all already ready in there.
No, I used the Python. I think it's kind of the same thing though. Yeah.
I think it's the same thing.
Yeah.
It's just mind blowing, and I think honestly, it shows a lot of foresight from the Earth Engine guys to, enable this kind of implementation. Like, I don't know, when they thought about the platform and they were like, oh, do we want to run like computer vision models one day, or do we want to be able to do like piecewise regressions over big stacks of pixels? They went the pixel stack way.
Yeah.
And I think it really paid dividends.
And what it makes me think of too is how much actually they optimized for a particular set of trade-offs in the like spatial, temporal, spectral domain. So just to take a step back for a second, it's like with Landsat or Sentinel-2 and trying to do like urban expansion or deforestation or gold mining or, all these things where it's like you have this before and after kind of, and you have this transition period. With these 30 meter, these 10 meter pixels, what you get is, it's not that spatially precise. So then to do this kind of detailed mapping, what you have is, and these things typically aren't like truly instantaneous, right? Like they take some time to happen. And so you have this actual transition period that you can measure at these 30 meter or 10 meter pixels, where it's like the NDVI is like rolling off. Decreasing. You know what I mean? It's not like it's not like plummeting. And so and I feel like that's so, because like sometimes I think about like, oh man, like stacks have SkySat, like we could be doing Landtrendr, CCDC on stuff like this, but actually it actually doesn't. I actually think some of the like underlying assumptions don't work that well for the high res, because it's like you don't have this mixed pixel thing. You don't have like co-registration taken care of. You don't have like the radiometric stuff taken care of. So actually your time series is going to be like kind of garbage. And so it's not even the right tool. But
interesting.
But in some ways it's like now that we have all this high res, people are like, and I feel like I fall into this trap too of like, oh, the high res is the place to go to see the thing that you need to see. You see it. It's
even
there.
Over long times, or just like for general change detection.
For just like general change detection, but I just think because of the high res, we undervalue the information and the trajectory from like the Landsats and the Sentinels. Yeah,
But
I don't know.
But I wonder if that's also just like Earth Engine in general being undervalued. Because like doing this outside of Earth Engine is, I mean, it just seems like it would be a nightmare. I don't know, maybe Planetary Computer really enables it, or
I don't think it does.
I just feel like I think Earth Engine is still kind of underrated. And people are still very stuck in like the CV, like how do I deploy a UNet on this platform?
Yeah.
So maybe it's a result of that. Like,
I think I was trying to make a point that was like, regardless of the implementation or the platform, it's almost like we've forgotten the approaches because of all the new data and constellations.
I see.
Do you know what I mean? It's like, because we have Planet and all these other things and daily imaging and 1 meter and 50 centimeter and 3 meter, it's like, who needs the like Sentinel-2 or like, but because Sentinel-2 and Landsat are so radiometrically accurate and have more spectral resolution, and you can calculate all these indices like, NBR or stuff in the SWIR bands or whatever, and look at transitions over those, then, I don't know. It's like we're kind of like, we're missing some of, we're just underutilizing some of the temporal information that can solve what I think are like still timely problems. To do mapping now. I think
interesting.
Do you know like I thought this Cuba thing I just worked on was a simple example of how this could be useful, which is let's say you're trying to compare like nighttime light intensity from time A to time B, or like before and after. I feel like this is the classic like look at this place go dark kind of thing. But with the dense time series, you can do better because you can characterize what normal looks like. And then you can look at what now looks like in comparison to normal, taking the variance of the baseline into account. And so that's not even something like Landtrendr, right? Or anything like that, but it's a way in which you're using time series to make a more robust statement about the thing you're trying to map than just like before, after, brighter, darker, done,
Yeah. Right.
And so I guess I'm just finding more opportunities to use that is what I'm trying to say.
But I mean, I guess, I don't know. In the context of news, do you think that's like a more like a stronger statement? I guess like this is darker relative to where it was last year versus this is darker relative to the last 5 years.
Yeah, so I think that was useful for this Cuba piece we just did because Cuba is a place that has had grid instability for a long time, and so it wasn't like if you look in the time series at a particular pixel, there's already variability because the energy grid was already old and they already had supply issues and all these other things, and so there were already regular blackouts, and so it's actually not actually right to just do a before after because
you could pick
exactly
you could pick a
you can
time
just get
to
lucky
show
with
whatever.
the pick, right?
Yeah.
So you actually need the at least. I mean, you don't need
the fluctuations,
but capturing the variance of the fluctuations is actually something meaningful. So that when you say there's a difference, it's like it's a difference normalized by this variance. And
for sure,
in a place like the United States that doesn't, the grid's a lot more stable, this doesn't matter. But this is I thought it was a cool example where it actually does matter. It's a simple way to use time series data. I don't know.
Yeah, no, absolutely. Right. It's true that if the baseline is unstable to begin with and you're trying to make a statement about like, oh, it's even worse now, then you need a lot more observations to make that statement rather than just like, oh, it's darker now. It's darker compared to this time point.
Exactly.
So it's more context for your statement. Yeah.
I was thinking it would be cool to talk through some of the stuff that like Alice did, and maybe you worked on too, like the Bayesian updating stuff
Okay.
for like deforestation. Like,
Yeah.
I don't know. Do you want to like talk about that?
I mean, definitely mostly Alice. So
Sure. You can
I
take
mean,
the
I could
credit
go
though.
get her right now.
No.
So I think that was interesting. Yeah, I mean, I guess this is super relevant. So I guess that was interesting because it's pretty much exactly as you described it, right? Like you have some historical record
Yeah.
and you have some assumptions about this historical record, like, oh, it's like roughly Gaussian or something like that.
Yeah. So in the
And
case of
therefore I can
deforestation, it's like you have a forest mask. You know where your forest pixels are,
yes,
kind of.
which is actually that's a huge part of the practical problem.
Yeah.
But like for all intents and purposes,
Right.
okay, these are the main forest pixels.
The non-deforested forest, stable forest,
primary forest, I believe.
forest.
Man, I feel like such a fraud talking about Alice's work, but yes, primary. Let's just say
you were on the paper,
forest.
Right?
I was on the paper.
There you go. So you're qualified.
Yeah. Okay, so you have a set of like you have a set of pixels, a bunch of locations where a forest mask that you start from, and then once you've established that, like, okay, these are the pixels that I believe are forest, you go back in time and you collect as many observations as you can over them to sort of parameterize how forest pixels behave over time, because there's a seasonality component.
Sure.
Ideally,
so pick like 2 or 3 years from Sentinel-1, let's assume.
Yeah, definitely Sentinel-1.
Yeah.
Because most of the locations you're interested in monitoring deforestation in are tropical.
But this is totally agnostic to the sensor, right? Like this works for anything, theoretically.
This works for anything. It just so happens that because of geography,
right.
You kind of want to be able to see through clouds for this to collect enough observations to set like a baseline.
Yeah, so you captured a mean and standard deviation over n number of years with your primary forest mask.
Yep. Yeah, and then for each pixel, now you start like collecting new observations. So you have like a cutoff period.
So that was like your prior, right?
Yep.
In the Bayesian way of the world.
Yep. Yeah. And so that's your prior. Like this is what forest is. It's a Gaussian with a mean of this and a standard deviation of this, and therefore, for every new observation, we can calculate like a probability that it belongs to this forest distribution for each pixel. Right. And honestly, I feel like a lot of the. I think what was cool about this implementation and this algorithm was that it was made to be operational.
Right.
It wasn't just like, okay, you just do this and then you go and then go and choose your threshold at some point and here are some like rock curves or whatever.
Right.
Like the algorithm, as far as I remember, was really chosen to be operational. It was first developed by people at a company called Satelligence, and it was just basically like, okay, you're going to keep recording this probability and you are going to define a threshold, but you're going to collect there was like an operational aspect to it where it was like you first flag a pixel if it's dropped below a certain threshold. And then if it stays below that, I mean, I guess this is kind of like what you were talking about with the NDVI rolling off, right? Like you first like flag when the backscatter starts dropping because there's less, fewer leaves to
but you don't
reflect
fully
back
make your decision
radar
yet.
signal. No, you just flag it. And often what you would observe is like, oh, the pixel jumps back up.
Yeah.
Or, it was just, there's stuff going on that you're not aware of, or your seasonal correction wasn't good enough.
Yeah.
And then you continue monitoring. Yeah, I think the whole idea was like you monitor the pixels and you need to do this sort of like accumulation of alerts. And then once you're past like 3 alerts, like you assign it. And so...
And then once you assign it, you can actually go back in time and be like, what was the exact time now that I'm sure that I've assigned it to this thing. You can go back
Yeah.
and like adjust the date,
Yep.
for example.
Yeah. And I'm not sure that was ever Descartes Labs' focus, like year of or exact time. I think there was like a near real time component to this. Like, I wasn't really aware of the details with clients and stuff, but I got the sense that this was
you never worked there.
There was a detection. I never worked there, despite.
But bringing them up every 5 minutes.
Yeah, exactly. Hey, I mean, they were my introduction to Earth observation, and this is an Earth observation podcast. So and so what was it? So another thing that I remember is that part of what. Okay, so Satelligence had like implemented this algorithm purely based on backscatter.
Yeah.
And I think those observations were available. They were under the name RAD, RADD. I can't remember exactly what this stood for. Those are the RAD detections. They're based on the same algorithm.
I think it's like radar deforestation detections. Something like that.
Yeah.
Sorry, maybe.
That sounds right. That sounds right.
Yeah.
And so what I remember was that actually those detections were fairly noisy.
Yeah.
You're kind of treating it like a purely temporal problem.
Mm-hmm.
And there is some spatial information, I remember, because the seasonal correction you did would be like a group of pixels instead of like a single pixel, right? So you are incorporating some spatial information that way.
Yeah.
But they were pretty noisy. And I remember that what made Descartes Labs' detections a lot less noisy was the incorporation of coherence.
Right.
And so I remember working quite like Alice was working quite closely with Matt Califf at the time, and the incorporation of just like this sort of like spatially smoothed signal over which you were doing the same temporal monitoring just made the detections in like it was night and day. Like they were just so clean. You were just losing all of these like single like random backscatter detections where like, oh, I don't know, maybe a leaf turned and now all of a sudden the Sentinel-1 signal is so much higher.
For the coherence calculations, what are the baseline periods as you roll forward in time? Like what's the before and after to actually do your INSAR and get coherence? Is it like a fixed prior baseline and you just update with the latest Sentinel-1 acquisition, or is it something else?
Yeah, I think it is fixed. I mean, it's kind of similar to the backscatter, and the assumption is just that you're using pairs instead of single observations. And the assumption still holds that like, bare ground is more coherent than vegetation, and therefore you would expect to see, and I think you did see this sort of like rolling or increasing of coherence over these areas that were being deforested. So when you said you wanted to talk about time series, I didn't even think about this, but actually this is just I think this is a great example and application of this kind of work where all the parametrization was like super simple. This is a Gaussian, mean and standard deviation.
So with the Gaussian is a big assumption that in the posterior, you got the new observations coming in, right, in your operational system. So the assumption there is that every observation that you get is independent, which is not always the case, especially with a lot of these sensors. I think that's probably it's probably a bigger problem with stuff like Sentinel-2, because if you get if like atmospheric correction goes wrong, or you get stuff like that can make your observations coming into the time series not independent, or at least that assumption could fail. Maybe with the radar, it's like, I don't know, maybe there's like look geometry stuff if you're incorporating multiple relative orbits, but you're probably not if you're doing coherence anyways, right? So maybe it's fine.
Yeah, I'm actually not sure about this independence assumption. I think I think this was just so much better than any other potential solution that they had at the time. Like I think basically
And it's like you can design a real
like
system around it. Like you said,
yeah,
it really lends
you can
itself to
operationalize
operation.
it.
Yeah.
I think there was a huge amount of work about like I think there was a lot of work around the seasonal correction, harmonizing the time stack,
Right.
the co-registration, like making sure that your co-registration was really on point to be able to do this. Because if it's like if the pixels are drifting around even by 1 pixel, because it's on a pixel by pixel basis,
Yeah.
that can really screw up your estimation of the background distribution or the forest distribution. But yeah, I mean, I think this was the first time I ever saw this kind of algorithm being deployed at scale.
Yeah.
And I think it was also pretty obvious that like I don't know if this was obvious, but I just felt like the platform had not maybe necessarily been designed for this.
Oh, sure.
At the time.
Yeah.
Like this was actually, there were some, I don't know. It was not as smooth as you would think it was.
The platform was designed to raster. That's what it was designed for. Is like and get imagery as fast as possible.
Yeah, and this was just such like it was just such an orthogonal dimension.
It's way more of an Earth Engine style thing. Yeah.
Yeah. Yeah. And I don't know. It was, but I think you still needed. I mean, and this is why I brought up the platform earlier about like, oh, why is this like, why do people not think this way by default, or why does it appear they don't? And it's like this kind of global stuff wouldn't have been enabled by anything other than like a platform designed for it. You know, like this is the kind of thing you could have like written a nice paper about, like, oh, here's a region and here's another region and here's some nice plots. But like to actually operationalize it and then look at the results, I just feel like that you had to have something like that to enable it.
Yeah.
Yeah. And so let me flip this on this head. When you did the West Bank stuff, you used Landtrendr, and you looked like it was the greatest NDVI loss again for like expansion of built area.
Exactly, NDVI loss. I mean, I played around with different metrics like NBR. I think NBR is like one of the ones that people use a lot. Like there's a lot in the NBR time series for all kinds of problems, just like how there is a lot for NDVI. But yeah, I mean, because I've used NDVI for proxies for built areas before, like low NDVI and lots of impervious surfaces. That's a nice relationship. And so, yeah, it just felt obvious that would be the signal. And it's interesting too. I mean, you'd think stuff gets built pretty fast, but you have enough observations, even with Landsat, that even with stuff that's getting built, especially with like land getting cleared first before, before concrete is put down, you get the same roll-off in the NDVI time series.
And what time frame did you look at this over?
40 years. Yeah.
40 years. Okay, so it's like a big, I was going to say like, for buildings, maybe coherence is a stronger signal.
Oh, yeah. But we just wanted to look like back way further in time. Yeah. So that's why Landsat was the right thing. And we didn't really care about, or at least we decided that we didn't care about, when within the year it was. We just cared about flagging a year. And so, it was a very similar thing. Have you used, I haven't actually, I've been interested in CCDC and having a good application for it, but I haven't actually used it for anything real in practice. My understanding is that it's basically, with Landtrendr, it's compute an annualized metric. So for your thing, that might be a seasonal composite per year. Maybe it's composite across the whole year. You get to choose what makes sense for you. And then you have one value per year or per unit of time, right? It actually doesn't have to be a year. And then that's what you're finding these breakpoints in. CCDC, from my understanding, is like let's say you have a year's worth of observations, it's like you use all of them and you fit some harmonic model to that, right? To be like this sine cosine wave is my model of the year. And so you can imagine how this works really well for like, I don't know, fields and agriculture and stuff like that. And then you can measure basically deviations from that. Like,
Yeah. So I actually can't remember because there are pre-computed CCDC coefficients on Earth Engine. They only go up until 2019, I think.
Oh, really?
So I can't remember if I used those
pre-computed
or if I ran it.
Oh, that makes sense.
I think they
right. You just got to store the Oh, yeah, totally. It's just harmonic models. Yep.
So
from what?
So
like
CCDC,
Landsat or Sentinel or something?
I think it might be MODIS.
MODIS. Wow.
I think it might be MODIS because it's like, okay, you want more
daily
observations.
Right.
Yeah, you want more observations to characterize this harmonic model. And if you don't have a ton, then obviously your harmonic model is going to be less well fit. And the other thing I remember being kind of tricky about CCDC is like you kind of have to start from the beginning, or you have to start. So basically, and again, this is a long time ago, but from what I remember, it's like you fit the first harmonic model, and then you have to you don't have to start from the beginning, but you have to roll it forwards. Is more what I meant. Whereas like Landtrendr, you could you just separate out the years and you do each calculation within the year, and then you do the fitting, if that makes sense.
I see.
The way CCDC works is you start fitting, like you have a period for which you fit the harmonic model, and then I think you roll it forwards, and the error you're monitoring like the error between new observations,
like the mean squared error or something like that, root mean squared error.
The RMSE.
You got it.
Yeah, between new observations and the harmonic fit that you had previously.
Got it. That makes sense.
And I think once it deviates by a certain amount, by a certain amount and a certain number of observations, you fit a new harmonic model, and then you roll the model forward. So it's like a monitoring. It's almost like a break, more of like a. Well, I guess you can use it for retroactive analysis, and people do, but I feel like CCDC is like meant more as like some sort of like operational monitoring algorithm, rather than a retroactive. What are the broad scale trends that Landtrendr might be.
Yeah, got it.
And so,
it's for more maybe more jumpy stuff.
I think it's for more jumpy stuff, but also when within the year did this happen. More of like there's been a change, we're going to send someone out there or something like that, and I think there's been a few like extensions on top of CCDC that are like this sort of object based stuff, which is like you look at like groups of like super pixels instead of single pixels, and a lot of stuff has been done by, I think it's the University of Connecticut. They actually have some Earth Engine apps.
Oh, I think I've seen some of these. Yeah,
where they're like running like actual change detection monitoring type stuff over CONUS using these types of algorithms. Cool. But I hope I got that right. Well, I guess our listeners can correct me if I got it wrong.
You just bullshitted for 5 minutes.
That was what I remember of CCDC, and I seem to remember that it picked out the well pads better than Landtrendr did.
That makes sense.
Like the well pads themselves, but it's just like it's pretty noisy, especially if you're trying to apply it to like one observation a week plus clouds.
Yeah.
That can be pretty noisy, to really capture this harmonic. Like
I was just thinking like with a Landsat style thing, it's like how good is that harmonic model with clouds and stuff?
Yep. Yeah, but I also remember the results being a little noisier than Landtrendr when I looked at them for this kind of stuff.
So Landtrendr, you're basically you're sacrificing some of this temporal resolution for this like smooth signal continuity thing.
Yeah, but honestly, I kind of feel like near real time is a lie anyway. I don't know. I mean, it depends on what you're trying to do. But I just feel like the Landtrendr analysis of like these long-term changes feels, I don't know, just from looking at the two outputs, I was kind of like, oh, this is better. There's better segmentation.
There's better segmentation.
Temporal segmentation.
Yeah.
That was just looking over New Mexico.
Yeah.
So it could be different somewhere else.
And maybe you can make the argument that with Landtrendr and stuff, you know, you're not doing anything. You can't do anything timely. Like you can do kind of historical analyses and update it to the current time. But yeah, like you said, it's like I feel like there's no hope of a near real time style thing with Landtrendr.
Yeah, I mean, but Landsat and Sentinel in general, I just feel like, I don't know. The near real time thing is like, first of all, it's within a week. If there's no clouds, then there's so many asterisks.
So you shouldn't even be using it for that kind of thing.
Yeah. And maybe that's what drives people towards like this high res, like I can task a satellite or I can get like the latest and greatest and I know that it's
so that leads me to ask you about another thing that I think you know about that is more about this, or maybe could be more about this like high res or wanting to do a near real time thing, but wanting to do better than a before and after difference or a before and after visual analysis, which is ACD. So, you know, I feel like anomalous change detection. So, I mean, I feel like this is something that, at least from my understanding of the formulation of it, which is that like you need to have enough pixels to like characterize the unchanged distribution, right? And then
the uninteresting changes.
Right. And then you Mahalanobis distance or something like that to flag anomalous pixels. And I was thinking about it recently because I realized that with the tent detection stuff, which was on SkySat, that started, at least the way I started, I was like, let's take a difference. Doesn't work because the seasonality is all different and the radiometry is all different from all these acquisitions. But actually, maybe my next step should have been ACD to try to solve that. I think there's a lot of reasons why the thing I ended up doing works better for scaling and practical reasons, but it's actually not something I tried. I didn't think about it at the time. But yeah, I don't know. Do you think that could work?
I'm always of the opinion that if you know what change you're looking for, then look for that change directly. Yeah. So I think what you did makes a lot of sense.
ACD is more like I want to find all possible changes here.
It's almost more like maybe I know that like the tents are in the minority and the only two acquisitions I have are like very different seasons. So there's like a very strong background change where like vegetation's appearing as well. And I don't care about like broad scale changes or I guess pervasive changes. What I care about are the anomalous ones in the image, which generally tend to be related to human activity. Yeah. And so that's the kind of case where this algorithm would shine.
Got it.
But it kind of depends on, I don't know. So the algorithm's kind of finicky because, and it's kind of beautiful and simple in some ways because it just, treats the before and after as like part of the same, like a joint distribution.
Right.
And then it says, okay, like it's like the result is baked into the formulation.
Yeah.
Like, I don't care about all changes.
Yeah.
I just care about changes which are mathematically distinct from most of the other changes in this joint distribution that I have in my scene, and therefore, and that's why it works so well because it's like almost like tautological, it's like and so the anomalous part does a lot of the heavy lifting
Right.
in the descriptions. And so if you just imagine like, okay, like our pixels, our before and after pixels are like smushed together, they form
Yep.
this like joint distribution.
Yep.
There's a centroid to the distribution. Actually it turns out that like, you know, Gaussian or a fat-tailed parametrization of this joint distribution is like fairly accurate or fairly general. And so as a result of that, you can parametrize like the spread of this distribution of before and after pixels by a covariance in like every single spectral dimension. And therefore pixels which are not only far from the centroid of the distribution, but far scaled in terms of like scaled by the covariance, are by definition, are by definition anomalous. Like if I'm like in a particular direction, but I'm like 3 covariances in that direction away, and most of the pixels are like 0.5 covariances away, and I'm like anomalous, you know?
I can see how this would work really well for really high, a lot of spectral dimensions.
Yep. Yeah, I think it was
like
initially developed
data?
for hyperspectral.
Oh, okay, cool.
I think it was initially developed for hyperspectral. And again, actually, our friend Matt Califf wrote a paper on how if you don't have enough dimensions, this measure kind of collapses a little. But I think the subtlety in the formulation is like, okay, what if all of my pixels in the before scene are dark, and I have like 1 pixel that's really bright.
Yeah.
And then all of my pixels in the after scene are maybe a little less dark.
Yeah.
Or like there's like some other change in some other direction, but that bright pixel stays bright. Like a building that's still in both.
Yeah.
Within the individual image of the before and after, that pixel is actually anomalous.
Yeah.
Right? Like if you just ran a normal anomaly detection algorithm on the scene, that pixel would be anomalous, but it doesn't change.
Yeah.
Or, you know, it doesn't change relative to the changing background, for example. And therefore, it's not an anomalous change. And so you get this like measure, which is like anomalousness in the change image is distance from the centroid of the distribution scaled by the covariance. But then you actually subtract the individual anomalousness of the same pixel in the before and in the after scene. So like you don't care about actual anomalies, you only end up caring about anomalous changes.
Yeah.
Right? So even if a pixel is anomalous in the before and anomalous in the after, it can be a non-anomalous change. Yeah, this is kind of difficult to describe with words. But
yeah. So I guess this breaks if you're in a situation where there's where the majority of the pixels have changed. Like doesn't this kind of, with the joint distribution, doesn't it kind of assume at that point that most of the pixels are normal?
Well, so if most of the pixels
not normal in the Gaussian sense, but yeah.
If most of the pixels change, then the actual anomalous change is the pixel that hasn't changed.
Sure. But I guess yeah, but I guess practically speaking.
So, but that's the thing, right? It's like, what are you looking for? Right? Like if most of the pixels change because snow falls, right? But there's like one spot where like the snow is melting because there's like human activity or there's heat or something like that.
I see what you're saying.
This algorithm is designed to pick out that thing, even if it looks the same in the before and after, because it's like, it's a measure that's relative to the background by definition because of the anomalousness. And I know it sounds silly, but honestly, if you just apply it and you look at a bunch of results, it's insane. Like it's just because it's baked in so often you're like, oh, that is actually an interesting change. And I wouldn't have picked that out in the image. So this is definitely meant again for sort of like I would say this is sort of very operational minded, right? Like you have an analyst, you have a large area you're monitoring, you can only surface like a set number of examples to the analyst to review. Which examples do you surface, right? Like what are the interesting things that might have happened, given that we don't care about like large scale background changes. I think the thing that's tricky about this algorithm is that by definition, the background depends on the size of area you choose to calculate it over.
Yeah.
Like something cannot be an anomalous change at all when you're zoomed in on it because the thing is the background. But if you zoom out, the thing becomes anomalous.
So you have to think about what scale you're running this at.
Yeah. And I've not really seen anyone operationalize this that well, or I mean, not publicize it, right? You probably have to do some like tiled measure.
Yeah, like run ACD at different zoom levels and then consolidate those results somehow or present those results in some way.
Yeah. And so the other thing is like, okay, ACD returns, it returns like an anomalousness measure, which is like Mahalanobis of the joint minus Mahalanobis of the before minus Mahalanobis
like
of the after. Like
taking out the absolute before and afters. Yeah. Mm-hmm.
But then you still have to decide, like, what is my definition of anomalous? Is
like
it
your
the
threshold?
Top 5? Yeah. The top 5 percentile? Is it the top 1 percentile? And after that, there's still like zero information for you. Like, I mean,
it's just like, this is anomalous. Now go figure out what it is.
Exactly. The only information you get is where, right? Like, that's the only information you get. And so I think there's like some interesting ideas around, okay, like let's get all the anomalous changes and then maybe let's run like a land cover change over them to like categorize them into land cover transitions and then further.
I have a question for you. What if you're in a fairly zoomed in area where every land cover transitioned to something else? So the fields became fallow and the wetlands became dry and the buildings were burned down. What would ACD result in?
That's a happy thought.
In this happy place.
In this happy place.
No, but okay, there's some basis for this being real, which is, again, going to like war settings. You look in these places and apart from all the seasonal stuff that happens, which is real, I mean, all the seasonal differences that this algorithm is pretty good at not flagging for all the reasons you just described, you have multiple land cover transitions in war zones. Like buildings turning to rubble, new structures appearing where structures didn't exist, fields going fallow, craters, like you have you have like 5 or 6 land cover transitions that are happening at once. So if I ran ACD on that, what is it going to flag?
So it depends on the size of the tile you chose. Like it depends on the size of the area and the size of the tile you chose. But if it's like a very chaotic environment where all of this stuff is happening, then it's just going to, like, again, it's just going to mathematically spit out like what the...
Yeah. I guess my intuition is that it kind of wouldn't spit out anything with a high threshold. And then as you went down that threshold, it just like kind of everything would ring up.
Yeah.
But maybe my intuition isn't right. I haven't actually run this before, so I don't have as good of a sense.
I would not use ACD to track like broad scale changes.
Yeah.
Like in the specific example you gave, like, okay, fields are turning fallow, right?
Yep.
But this one field didn't. So someone is still cultivating it or something like that. Like, or all the fields have been harvested or burnt down, but this one was not, or the converse, like all of the fields are like experiencing their seasonal NDVI changes, like, greening up or whatever, but this one field was already cut down and burnt, right? Like that's the kind of change that I believe ACD would like point out to you. Because I think a lot of the changes that you described are like maybe pervasive changes.
Yeah.
Right? Like the whole system is changing together.
Yeah.
Now, the craters, I think, would be different, right? Unless the whole city is like one big crater. Right. And so I think what ACD would be good for is like accounting for differences in like maybe some haze, some slight haze,
Yeah,
or
yeah,
like
yeah.
differences in illumination, and just like, but there's like a huge crater where a building used to be, or something like that, or like a burn scar or something like that. I'm not sure I would deploy it over a large area. Well, I would because it's cheap, but I'm not sure I would expect to see, like, oh, here are all the things that I care about. Because, like, again, the question would be like, do I care? Am I looking for craters? Because if I am, I should just look for them.
Yeah.
Or am I looking for like strange? Like, I think it usually boils down to human behavior.
Yeah.
Like, am I looking for some strange human behavior that could be reflected in the before and after?
Right. And
Yeah,
is ACD is it, how sensitive is it to co-registration errors? My sense is that it would be very sensitive to that, but is that true?
It is, but there's actually another algorithm called LCRA, Local Co-Registration. I think the A probably stands for anomalousness. I can't remember the exact acronym, but so this is something that James Thaler, my old postdoc mentor at Los Alamos National Lab, who developed the algorithm. I think they realized this very early on that like, okay, if we just shift a pixel by a pixel, like the anomalousness scores are totally off, because it's really important that the scores like stay the same. And so I think there's an algorithm where they actually manually shift. They shift the algorithms around a certain window. They shift the pixel around a certain window, like the 9-pixel window.
Yep.
They shift it. They calculate anomalousness scores for each shift, and then they do like a reduced region.
Yeah.
And they say like
min or the max.
They take the min.
Yeah.
They're like, whatever the minimum anomalousness score was, as we did these shifts. And obviously this doesn't account for like non-linear, like if one part of the image is shifted in a totally different way. And so that reduces the scale at which you can pick out the anomalous changes, right? Because now it's
you're
kind of
losing
like
resolution,
a little blurrier.
basically.
Yeah, but you're more sure that the thing you actually ran is legit.
Yeah.
Yeah.
Cool.
So
I feel like this is something that I have lots of use cases for. Like, I am often in situations where I don't really know what I'm looking for, but I want to look for something that is interesting or has changed. And so I feel like I have to, this is like an Earth Engine. I'm surprised there isn't at least I haven't found an Earth Engine implementation of this. I feel like this is kind of like, would scale really well in Earth Engine, maybe.
There is no Earth Engine implementation. I don't know if it would scale really well, because you do have to drop out, like if there's a cloud, you kind of drop that whole, that pair of pixels out.
Oh, yeah. I mean, that's fine. That's just masking, right?
Masking, and then you calculate a covariance. There's probably a Mahalanobis distance function, I bet. And then you need to do it on the before and after. I think this would have to be a reduce region. Can you get a raster output from that?
From a reduced region? No, that's going to return a vector. But then I think you can
basically you would have to
turn it back into a raster.
Like, this has to be a function that operates over like the bounds of the image, or like you define a vector over which you're going to run this.
Like you should have a GeoJSON of where you're going to run this.
Yeah. Yep. Which makes you think reduce region, but
you're gonna have to think about it. But I feel like this would be really nice first
pass. Yeah, I think this is a great first pass at like anything, because it's just like helps you triage the pixels.
Right. And like image differencing just never works. NDVI differencing does, but image differencing does not.
Yeah, I mean, it's just too
noisy.
But okay, here's the well, maybe this is not crazy, but the before and after don't really have to be from the same modality.
Right. Hmm.
You know, yeah,
Yeah.
it kind of depends on what changes you're interested
I see what
in,
you're saying.
right?
Yeah.
Like the changes you're interested in have to be able to be picked out by both modalities.
Yeah. Yeah.
But
Yeah.
like you could, if you resampled to 30 meters, you could do
Uh-huh.
this between, or downsampled Landsat to 10, you could do this between a Landsat and a Sentinel image.
Yeah.
And
Yeah.
it would,
Yeah.
because like it doesn't even care about what bands,
Yeah.
because you just concatenate the before and after,
Right.
right? Like that's
Right.
how you create this joint distribution.
Joint distribution. Right.
So, and that I think that's interesting. Like we did some
Mhm.
experiments on this, and this was again in paper mill days. But I
That
think
you
it's
look
like
back on so fondly.
I look with much fondness, but I think I really like it because I really like algorithms where like the baseline is like you just can't do it.
Yeah. Yeah.
Like, and so this algorithm allows you to do something that makes more sense than like differencing a normalized
Yeah.
Sentinel-2 and a Sentinel-1 image.
Yeah.
But you can actually pick out some interesting changes between modalities this way. And I think the general idea is like, okay, we could just run this on every pair of scenes of like every sensor. And get like this gets us closer to like the near real time changes.
Yeah.
And like, like some of the changes aren't going to make sense, but it's like, what were you going to do anyway? You were going to wait until the next acquisition, right?
You're just going to look really hard at it.
You got something to look at now. You got something to look at between the two images.
Yeah.
And doing this by eye, like trying to pick out, it's like hold on, let me get the right name because it's different between the US and the UK. Is it
Waldo.
Wally? Okay, in the UK it's
Waldo?
Wally. Where's Wally?
Where's Wally?
Okay, it's like where's Waldo?
You don't have to Americanize it for us. You can stick with the UK version.
This is like where's Wally? It would pick out Wally very easily. So yeah. Yeah, maybe that should be a demonstration.
This is I feel like this is worth trying for me. Yeah.
Totally, and it's just so inexpensive.
Right.
Like, okay, don't pick too big of an area because then inverting that covariance matrix is tricky.
Yeah,
but
I'm curious to try this on some high res where the co-registration is not good. I wonder if that pixel shifting thing works because I kind of don't care that I lose some resolution in the output. I care more about just knowing where to look in this high res image. And so, yeah, because my guess is, these are my own problems. I'm talking out loud, but my guess is even after trying to do some co-registration fixing before the fact, you still have some residual errors.
Mm-hmm,
so then you do your 9-pixel sweep and do the minimum of the scores of the anomalous scores. But
it doesn't have to be 9 pixels. Like, you can make it bigger if you're not.
Yeah, for sure.
And actually, I just realized that actually this does account for non-consistent shifts across the image because you choose the best one per pixel.
That's right. So it's like you have this 9x9 window, you slide it by 1, and then you're doing a minimum every time. So actually, if you get to the other side of the scene and the pixel is nonlinear, then it actually should work. Yeah, nice.
Yep. Yeah. And it's like, again, it's like, okay, it's like a little brutish, but it's also super simple, just like the idea of the detector in the first place.
Yeah.
And I really like these like simple solutions.
I mean, who doesn't?
Oh, a lot of people like complexity.
Embedding, simple solutions.
So, yeah, actually, there was a paper that just came out. I haven't read it in depth, but I was overjoyed
can you do ACD
to find
on embeddings? Because can't you just do the joint distribution in embedding space?
Yep. Mm-hmm. Yeah.
Is this the paper? Oh, no.
No, this isn't the paper.
Okay.
I tried this. I didn't get a ton out of it. I think I didn't do it over. This was like over Tapajos.
So you did ACD. You did ACD over 2 embeddings.
Tapajos.
Oh, in Tapajos.
When we were doing the before and after change thing.
Gotcha.
And I think again the problem was like viewing the results and making sense of them. Like what?
So you got the scores
interesting.
and you were cutting a threshold and looking at them? I don't remember you trying this.
Well, it just didn't really pan out. So
Got
I
it.
was just like, oh,
Just didn't even report your results.
Didn't even. I mean, I'm sure I mentioned it. I'm sure I was like, oh, I'm going to try this. And you were like, oh, yeah, totally cool, Chris. Let me know how it goes. And I was like, yeah, it didn't work out.
Okay.
But I do think this could be interesting. But again, it's like choosing the right region and like, what are you actually looking for? Like, what are you hoping to see? But I think this could be interesting over.
But why doesn't our hyperspectral argument hold for embeddings? Is it because
I think it does.
It does. Okay.
I wasn't able to explore the results, and I also think the changes over Tapajos were mostly like there was rainforest here.
Yeah.
You know, we can kind of already see those. But I do think that like someone, I mean, just talking about this out loud now, like if you took 2 years of Alpha Earth,
exactly what I was thinking.
You ran this,
yeah,
I bet you would see something interesting by definition.
Mm-hmm.
By definition, it would be interesting.
Well, by definition, it would be anomalous. Might not be interesting.
Well, you know, it turns out that if you pick like just a decent sized region, those things tend to be, in my experience, I don't know, it's just mind blowing how often this formulation just results in something interesting. Because it's like, oh, this didn't change the same way as everything else did. Which is interesting, you know, by definition, or very often, I guess. So yeah, someone should totally go and do that.
Yeah, that's actually
and implement it in Earth Engine.
Yeah.
Yeah. So the paper was that they had done like some compression on foundation models. Both, I think someone's done this experiment for like just computer vision. Like if we compress Dino v3, like we try and reduce it down, like how much ability does it lose on these benchmarks
Dino
relative
v3
to
Flash,
the level of compression? Something like that, yeah. Something like that. I'm not sure that exists, but you got the right idea. And they found that, and it turns out that like this computer vision foundation models, they don't compress that well. Like the features they learn are fairly complex, and therefore if you try to get rid of them, they're fairly high. You know,
but when you say compress, you're not just dropping stuff out. Like you're doing something else. Like
they called it slimming. I don't exactly remember the mechanism by which they slimmed. Like maybe it was distillation or so, but the result was that they could achieve 70% of the performance on like a bunch of Earth observation benchmarks with a model that was like 1% the size.
Wow.
Which they could not reproduce with computer vision models. Like it doesn't scale. Which is again an indication that like, you know, things just aren't that complicated visually.
Yeah.
In Earth observation. I can't even remember why I brought this up, but yeah. So that's ACD. I think there's a lot of interesting things. I think people don't really, you know, it's like kind of a hard thing to write a paper about.
Here we go again.
In academia. I'm just saying, like, why is this like beautiful, simple solution not have more stands? And I think it's like, it's hard to write a paper about it because then you need to demonstrate it over specific changes. Like, oh, look at this burn scar. We picked out this burn scar. But
it's by definition like not a domain specific thing. Doesn't solve a specific thing. Yeah. It's just arbitrary.
But to publish the paper, you have to produce the benchmark results, right?
Yeah.
And so you're kind of like, oh, look at all these changes it found. But if I was really looking for those changes, I would just monitor for a burn scar, you know, like, so that is the problem. Like, this is a really good algorithm for like, like I just want to check this area out. I think it's really good for that. So yeah.
Do you think, last thought about ACD is, do you think that if you had SAR data before, after, but different geometries, like different look angles or different ascending, descending passes, and that was the before was ascending and the after was descending, in the joint distribution formulation, it should be robust to that, right?
Yes, but I would still run the local co-registration adjustment.
Yeah.
And also with SAR, so Matt wrote a paper about where he looked at Burning Man in Sentinel-1, and because you only have 2 polarizations or 4 or whatever, it turns out that you don't get a very good measure of anomalousness. And so what I would do in that case is not only
is this like the underdetermined case you're talking about here?
Yeah, but I would also, what Matt did was he created windows of features. So now each spatial windows.
Got it.
To increase the dimensionality of.
So you take a window, you concatenate all those values, that's a feature, and you take a different window, you concatenate that's another feature type
so
thing.
So now you have 9 features instead of 1 per channel.
Huh.
Yeah, and then you do the anomalousness registration on top of that, I think.
Yikes.
If you're worried about co-registration.
That sounds like a pain in the ass.
The problem does blow up. Yeah. And then you're all of a sudden you're like, oh, I'm just running convolutions. I should use some sort of network to do this.
Yeah.
But yeah.
Wow.
Yeah.
Cool.
So yeah. Wow. Memory lane.
That's what I'm saying.
So you're gonna make an Earth Engine ACD package?
Actually, maybe I should. This sounds like something that I possibly could make.
Yeah, you should. You should.
I mean, I think I would use it, so maybe I will actually try to do this.
Yeah.
Or somebody out there will make it faster and give it to me.
I don't think so.
Nobody's doing this,
Nobody cares. It's not a foundation model.
Yeah.
Well, but it is kind of foundational, actually, which is kind of crazy. Anyway, I don't want to harp on about this, but it's it is foundational. It's just general change detection.
Yeah.
And in an interesting way.
Yeah.
And it's what's interesting to you might not be interesting to me. And it's okay, fine, let's define it with respect to the background then.